So we can see here that, again, our good old friend similar wave equation has popped up. X equals a sine omega t plus epsilon has come up. However, this can only describe one dimension, excluding time. So we're only talking about the height of a wave. However, what we really want to do is to define or derive, we're not actually going to derive it, but actually show an equation that relates two spatial dimensions relative to time. So when we're getting onto 3D waves. So the equation that we're going to be using looks a bit like this. We have y, so the y position relative to the x position and time is a sine of kx minus omega t plus epsilon. So yeah, it maps the y position to an x position at some time t. Now I am going to have to define a couple new variables here. So k is what's known as the wave number. It is essentially a rate of radians per meter. So obviously if the wavelength's really, really big, then k will be really small. So it's essentially how many wavelengths pass per full cycle. Well, relative to 2 pi in a sense. Then omega is actually one we've defined before. Omega is actually just the angular frequency, which is 2 pi times f. And in the next video, we're going to be actually utilizing this equation.